This is the line f of x. The slope of any line can be calculated using two coordinate values across the line. The first point is x, and the second point is x plus h, with h being any non-zero positive value. To get the slope, it's f of x plus h minus f of x all over x plus h minus x, which simplifies to h. This is also called rise over run. What if you wanted to find the slope of a line that's tangent to a point on a curve? Say on this curve we have point x. We can use the previously made formula to get the slope here by picking any value of h. However, as you can see, when h is really big, the line isn't even close to being tangential. But as the value of h gets smaller and smaller, it eventually becomes almost entirely tangential to the curve. Now that's where the concept of limits comes in. We could say for any curve, as h approaches to 0, written like this, the slope will become tangential to the curve. If you plug any function into this, the function you will get out of it is called the derivative, denoted using f prime of x. Let's do an example. Say you have x squared. Let's plug it into our original formula, x plus h squared minus x squared all over h. This evaluates to h in brackets 2x plus h all over h, which cancels out to make 2x plus h. Applying the limit, h becomes 0, and so the derivative of x squared is 2x. Knowing that the slope is 2x at x equals 3, we can use line algebra, and we can now make the equation for the line that is tangent to x squared at x equals 3, which is y is equal to 6x minus 9. The derivative has many applications, including uses in physics, economics, medicine, and more. And one more really interesting thing, the derivative of a function showing an object's position represents its velocity. Let's go outside. What if I told you I could throw this basketball right here in the air, then using its derivatives, find its velocity at any given second? Firstly, throw the ball. I'm going to use quadratic algebra to model this as a function. It reaches its approximate 4.56 meter peak at 0.965 seconds, and intercepts the x-axis at 0 and 1.93 seconds, and so we can make the following function to represent it. To find the velocity of this function, we need to find its derivative, which is happening on screen. So using its derivative, let's say we want its velocity at 1.7 seconds. It would be negative 7.19 meters per second. Even at its peak, where the velocity should be 0, the derivative satisfies that too. Notice how the next derivative again is equal to negative 9.78, which is oddly close to 9.81. Does that number ring a bell, especially in physics? The uses of derivatives get so much more complicated and yet useful. And I hope you learned something new today.